Welcome to International Advanced Subsidiary Level Physics Program. In this AS level, we have 3 units, Unit 1, 2 and 3. And in today's session, we are going to discuss about Unit 1, Mechanics and Materials. In this unit, we are going to cover one complete topic, solid materials. As you all know, in Unit 1, the assessment criteria, the duration is for 1 hour 30 minutes and the maximum marks for this paper is 80. You will be getting questions of multiple choice type, short answer type, calculations, extended questions and open-ended questions. And the first important topic that we are going to cover in this session is solid materials. Let us see what all the syllabus specification in this particular topic. The syllabus specification covers, starting with Hooke's law, the stiffness, the stress strain Young modulus, and some important terminologies like ultimate tensile stress, elastic deformation, plastic deformation, breaking stress, etc. So you all can see what are the important highlights and objectives of this particular topic. So in order to answer Unit 1 thoroughly, you need to be thorough with the complete concept. So in this session, we will be covering complete solid materials section. In order to start with solid materials, the first important concept is Hooke's law. What do you know about Hooke's law? When a material is subjected to force, it deforms or it undergoes change in length. The force applied or the stretching force is directly proportional to the change in length, but this happens within the limit of proportionality. So Hooke's law is perfectly stated as, within the limit of proportionality, the stretching force is directly proportional to extension. That is, delta F is directly proportional to delta X. To remove the proportionality sign, a constant is introduced where delta F is equal to minus K into delta X. This K is what we call the stiffness constant or the Hooke's law constant, and you can even call this a spring constant. By the equation F equals K delta X, the stiffness constant K will have the unit of Newton per meter, because the equation goes with K is equal to F divided by delta X. F is in Newton, delta X is in meters. So the stiffness constant as a unit is Newton per meter. There's a minus sign appears in the equation, but you need not bother about that minus sign for any of your calculation. It just indicates that the restoring force is opposite to the direction of the displacement. So according to the equation F equals K delta X, you could define stiffness constant K as force per unit extension. But if you could draw a graph of force against, if you could draw a graph of force against extension, it would be a perfect straight line passing through the origin. That clearly shows that Hooke's law is obeyed. In most of the past papers, you would have come across a question, state Hooke's law and state the condition under which the Hooke's law is obeyed. So here the condition is very well stated, it should be within the limit of proportionality. So what is this limit of proportionality? It's a point up to which force is directly proportional to extension. Or in other words, it's a point beyond which force is no longer proportional to extension. If you could draw a graph of force against extension, as you can see on the, it is a perfect straight line passing through the origin. How do you determine the stiffness from this graph? It is the gradient of the graph, because gradient is y by x, here it is f divided by x. So the gradient of the graph indicates the stiffness. Then what's the significance of area under the graph? The area under the graph here goes with the shape triangle. So, it is something like force against extension, straight line, but the area under the graph is a triangle. So, it is half F into delta x. This half F into delta x is what we call the elastic strain energy or the energy stored in the material. It will have a SI unit joules. You can even express this in Newton meter. And if it is a linear graph, directly you can use this formula to calculate the energy. But if it is a nonlinear graph, you can actually count the number of squares and multiply with area of one square. That is how the elastic strain energy is calculated. At this point, the important point that you should know is what is elastic strain energy. The elastic strain energy is the energy stored in the material within the limit of proportionality. But the stiffness constant, even though we call it as a constant, it is a constant property of a component, but it varies with the dimension. So, you will not be able to compare the properties of the materials with the stiffness constant. So, in order to compare the properties, we need to go by some common characteristics. For that, we are introducing some more additional quantities. Stress, strain, and Young's modulus. Stress is force experienced or force exerted per unit cross-sectional area. This stress strain will exactly explains the common property of the material. But before we move further into stress and strain, let us see what is this elastic limit. How is it different from a proportional limit? Proportional limit means it is a point up to which Hooke's law is obeyed. But the material is stretched beyond the proportional limit. There exists up to a point, the material regains its original shape and size when the applied forces are removed. That point is what we call elastic limit. And what happens if the material is stretched beyond the elastic limit? The material gets permanently deformed and it no longer regains its original shape and size when the applied forces are removed. You could see from here, during plastic deformation, the molecular bonds are strained to the point of fracture, making it not possible to return to the same state. So, it is very clear, within the elastic limit, the material regains its original shape and size when the applied forces are removed, but not beyond the elastic limit. But in order to compare the general properties of materials, as I said, we need to define some other quantities like stress, strain, and Young modulus. So, let us move on to that section. Stress. What is exactly stress? Stress is the force exerted per unit cross-sectional area. It is represented by the symbol sigma. So, the formula goes as F divided by A. So, what should be the unit of the stress? It is Newton per meter square, which has the same unit as that of pressure, so which could also be considered as Pascal. So, the SI unit of stress is Newton per meter square or Pascal. The next important quantity that you need to be familiar with is strain. Whenever the material is subjected to stress, it undergoes strain. So, what exactly is the strain? Strain is the ratio between the change in length and the original length. Since it is a ratio between lengths, it has no unit. It is represented by the symbol epsilon, which is calculated as delta x divided by x. So, it is very clear why it has no unit, because it is a ratio between two lengths. But for any given material, the ratio between stress and strain is a constant, and that constant is what we call the Young modulus of the material. Before we move on to Young modulus, you should be familiar with, according to your syllabus specification, the different type of stress and their corresponding strain. The different types of stresses, there are many different types, but for your syllabus specification, you need to be familiar with the tensile stress and the corresponding tensile strain, compressive stress and the corresponding compressive strain. So, what exactly is this tensile stress? Tensile stress is the stretching force per area of cross section. So, when a metal is subjected to stretching force or when the material is subjected to tension, it experiences tensile stress. So, tensile stress is a very important question, actually repeated question in Edexcel. Define tensile stress. So, you need to be very specific about the type of force. So, it should be stretching force divided by area of cross section. It also has the same unit as that of Newton per meter square. That tensile stress actually creates the tensile strain, which is increase in length divided by original length. The other type of stress that I have mentioned is the compressive stress. If the material is subjected to compression, the material undergoes decrease in length. So, the compressive stress is defined as the compressive force per unit cross sectional area, whereas compressive strain is that decrease in length divided by original length. Hope you all understood about the different type of stresses and their corresponding strain. Let us go back to that, the ratio between that is what we call the Young modulus. The Young modulus is stress divided by strain. But in most of the cases, you will be asked to prove that Young modulus is E is equal to FL divided by AX. With the standard symbols, Young modulus is represented by capital E, which is sigma divided by epsilon, whereas sigma is F divided by A, strain is X by L. So, you will get an equation E is equal to FL divided by AX. You can use this formula directly for your calculation. If Young modulus is asked, you can actually substitute the force, length, area and extension. But you need to be very careful when substituting the data. Sometimes the data might not be given in SI units. For example, extension is given in centimeters and you are asked to find the Young modulus, and Young modulus has a unit of Newton per meter square in SI units. So, you need to convert the extension from whatever may be the given unit to meters. That is very important in calculations. In all physics calculations, the final answer has to be expressed with appropriate units, then only you will be getting the full credit for your calculations. So, this equation derivation is very important. Show that Young modulus is equal to FL divided by AX, where F is the stretching force, L is the length, A is the cross sectional area and X is the extension. But when we start with the stress strain graph, if I could draw a graph of stress against strain, within the limit of proportionality, once again it would show a perfect straight line passing through the origin. How do I find Young modulus from this graph? Stress against strain within the limit of proportionality, once again it is a perfect straight line. How do I find the Young modulus from the graph? It is the gradient, because stress divided by strain. Then what is the significance of area under the graph? You can see stress against strain, perfect straight line passing through the origin. The gradient of the graph is stress divided by strain, which is Young modulus. But area under the graph is what we call the energy density. What is this energy density? It is the energy stored per unit volume. It is even defined as the elastic strain energy per unit volume. And we can easily prove that energy density is equivalent to half into stress into strain. So, area under stress strain graph is clearly energy density. What would be the unit of energy density then? If it is energy stored per unit volume, it should be joules per meter cube. But by this graph, you will be getting half into stress into strain, which could give you a unit Newton per meter square. Do not panic, Newton per meter square is equivalent to joules per meter cube. So, exactly the area under stress strain graph is definitely the energy density. So, this is all the basic things that you need to know under the section stress, strain and Young modulus. As I told you in the beginning of the session itself, in order to compare the different properties of the materials, you need to be familiar with some other terminologies too. So, let us see that one by one. It is very important. You all would have actually seen this particular graph in your textbooks and in your additional resources. Stress against strain graph. We all have seen up to limit of proportionality what is happening. What happens if the material is stretched beyond this limit of proportionality? As I told you in the force extension graph, till elastic limit, the material regains its original shape and size when the applied forces are removed, because bonds are stretched within the elastic limit. And you should know the clear-cut difference between limit of proportionality and elastic limit. Up to limit of proportionality, Hooke's law is obeyed. But up to elastic limit, the material regains its original shape and size when the applied forces are removed. So, until elastic limit, we can say that the material undergoes elastic deformation. So, what is this elastic deformation? Elastic deformation means the material undergoes change in length when it is subjected to force, but when the force is removed, it regains or comes back to its original, and that is what we call elastic deformation. But when a material is stretched beyond elastic limit, there it reaches a point, what we call the yield point. At this point, a significant strain is produced for the given stress, or you can say a significant extension is noticed for the given force, and that point is what we call the yield point. So, the yield point is what we call the transition point at which a significant extension is noticed for the given force. So, that yield point always comes just after elastic limit. You can look at the series, first limit of proportionality, then comes elastic limit, then comes the yield point. So, beyond yield point, when the metal is subjected to stress, it undergoes plastic deformation. So, what is this plastic deformation? The materials are permanently, the bond between the atoms are permanently stretched. So, when the forces are removed, it will not regain its original shape and size. It is permanently deformed. You could see from this dotted line, even if the force is removed, the material has some permanent strain. And if the metal is subjected to continued stress, at one point the material breaks, what we call the breaking stress. But if you look at this particular graph, there exists a peak stress that exactly determines the strength of the material, and what we call the ultimate tensile strength or ultimate tensile stress. So, what is this ultimate tensile stress? It is the maximum stress up to which the material could withstand without breaking. So, when a graph is given like this, you could easily identify what is the strength of the given material or what is the ultimate tensile strength. All these terminologies, the brief or the exact definition is repeatedly asked, so you should know. So, before we wind up, let us see the exact definition of each of these terminologies. Once again, limit of proportionality. It is a point up to which Hooke's law is obeyed, or the point up to which force is directly proportional to extension. Next comes the elastic limit. It is a limit up to which the material regains its original shape and size when the applied forces are removed. Then comes the yield point. It is a transition point at which the material shows significant extension for the given force. Then elastic deformation, then plastic deformation. That you know, elastic deformation means the material actually undergoes extension when the force is applied, but when the force is removed, the material regains its original shape and size. What is this ultimate tensile stress or ultimate tensile strength? That exactly determines the strength of the material. It is the maximum stress the material could withstand without breaking. Then you should be familiar with the terminology breaking stress. Breaking stress is the stress at which the material breaks. So, in order to compare the materials, we need to go with Young modulus, not the stiffness constant, because the stiffness constant is the constant property of the component. It varies with the dimensions, whereas the Young modulus is a constant property of the material. It does not vary with the dimension. For example, if I take a thin copper wire and a thick copper wire, the Young's modulus remains the same, but the stiffness is not the same. As long as the material is same, when you are asked to compare the components also, as long as the material is same, you should know that the Young's modulus remains the same, but the stiffness varies. So, let us see the next section. Sometimes you get a question not directly force against extension. Instead, it could be the axes are reversed. You can see length against force. But in syllabus specification, they have not mentioned length against force. What you have learned is only force against extension. It is a perfect straight line passing through the origin. This particular question is actually taken from a past paper. A sling is a long string made of metal. One end of sling is fixed to the ceiling. The force acting on the sling was varied by hanging weights from the other end. The graph shows the results. This is the length of the sling against force. Okay, as I told you in my session, force against extension, perfect straight line passing through the origin, the gradient of the graph is stiffness. If the axes are reversed, how do I get the stiffness? It is the reciprocal of the gradient. That you need to be very, very clear. If you could draw a graph of force against extension, the stiffness constant is F divided by delta x. It is directly the gradient of the graph. But if I draw a graph of extension against force, once again it is a straight line passing through the origin. But how do I find out k from this? K is definitely 1 divided by the gradient. The reciprocal of the gradient will be the stiffness constant. But if a question is length against force and it is not a straight line passing through the origin, does that mean that it does not obey Hooke's law? No, it perfectly obeys Hooke's law, because length is proportional to force. That clearly shows this particular thing is the original length of the spring. If you could subtract that, definitely this graph would be a perfect straight line passing through the, it will follow the equation y equals mx. Now in this case, the first part of the question you could see, explain whether the results follow Hooke's law. So the answer here is, it follows Hooke's law, because the graph clearly shows force is proportional to length, which means force is directly proportional to extension. But this next part of the question for 3 marks show that the stiffness of the sling is about 0.7 Newton per meter. Look at the graph, the length is given in centimeter, but the question is asked that 0.7 Newton per meter. So you need to convert actually the length to meters. So as I said, since the axis is reversed, you work out the gradient, then reciprocal of the gradient, you will definitely get this answer. That is why it's 3 marks. The conversion is very important here. So like this, you could actually come across several questions, but definitely if the topic solid material is thorough, you would be able to score like from 9 marks to 16 marks. Hope you all understood today's session and wish you all good luck.